Welcome to the Algebra 2 Structure and Method textbook series. This is on Chapter 7, Section 3, the discriminant. In today's lesson, you're going to learn how to determine the nature of the roots of a quadratic equation by using its discriminant. Before we start, you should know how to identify all the pieces of a quadratic formula: quadratic term, linear term, and constant term. You should also know how to simplify radical expressions. You'll also learn, obviously, what a discriminant is. Let's get started. For our warm-up, you can pause and restart the video when you're ready to check your answers. I'm going to show my answers now. Okay, how did you do? If you struggle with any of this, go back and review Chapter 7, Section 2. Now let's learn about some discriminants. We previously learned how to use the quadratic formula, where you can write the roots of the quadratic equation ax squared plus bx plus c equals 0 as x equals minus b plus or minus the square root of b squared minus 4ac over 2a. The expression under the radical, b squared minus 4ac, is referred to as the discriminant d, capital D, important. If you split the quadratic equation based on the plus and minus sign, you can see that we have two roots in the following form. And we can use the discriminant to find the nature of the roots of the quadratic equation without solving. To solve x squared plus 6x minus 2 equals 0, all terms should be moved to one side and the other side should equal 0. I'll find my values of a, b, and c and plug them into the quadratic formula. I need to simplify using the correct order of operations and find my solutions, which is negative 6 plus or minus the square root of 44 over 2. This can be further simplified, and we get our solution set of negative 3 plus or minus the square root of 11. Just keep in mind, your teacher may not require you to actually do that last step and split it into two answers, but you should always reduce the numbers within your solution set. Now, in this case, the roots are real, distinct, and unequal. Let's try another. Now, feel free to give this one a try on your own, and I'm going to start now. I'm going to find my values of a, b, and c and plug them into my quadratic formula. I need to simplify, again, using the correct order of operations, and I get to 2 root 3 over 3. Now, the square root of 48 minus 48, it's 0. So I basically have two solutions that are the same thing. Okay, 2 root 3 over 3. This is called a double root. To solve x squared minus 6x plus 10 equals 0, again, make sure everything's on the same side. My values of a, b, and c, a is 1, b is negative 6, and c is positive 10. Plug that into my quadratic formula. Simplify. And I have a negative number underneath my radical. My discriminant is actually negative. I'm going to simplify using our properties of complex numbers, and our solution set is negative 3 plus I and negative 3 minus I. Now, in this case, the roots are imaginary conjugates. The value of D can help us discriminate in three cases of solutions. If D is positive, there are two unequal real roots. If the discriminant is equal to 0, there is one double real root. And the last case is if b squared minus 4ac is less than 0, then you have two conjugate imaginary roots. We saw examples of each of those in our first couple of examples. We can also determine if a quadratic equation has rational roots by looking at the coefficients a, b, and c and reviewing the discriminant. If the discriminant is a perfect square, the square root of it will always be an integer, which means our roots will be rational numbers. For example, in the equation x squared minus 4x plus 13 equals 0, a, b, and c are integers, so this will have rational roots. Our second example, x squared plus 4 rad 2 times x minus 8 equals 0. Well, b can never be an integer in this case. It will not. We cannot say that it has radical roots. Now, you can also have quadratic equations with integer coefficients that can be transformed. Very good. If I multiply both sides by 3, basically, I have a quadratic equation with integer coefficients. So those will also have rational roots. So now let's try and use our discriminant formula. For example 2a, we have 3x squared minus 7x plus 5 equals 0, and we don't want to solve, we just want to figure out what kind of roots it has. Okay, my discriminant is negative 11, which tells me that the roots are imaginary conjugates. Example 2b, same thing. Feel free to pause and give it a try on your own. My discriminant is 49, positive and a perfect square. So this has these are rational roots and they're real and unequal. For this one, right away, I can't say anything about the rationality of the roots because I have 2 radical 3 as my b. So I'm just going to plug it in to get 16. And I know that the roots are real and unequal. Nothing about rationality. Final one. Now we can transform this equation by multiplying both sides by 4 to get x squared minus 10x plus 25. Then we'll apply our discriminant formula to get 0. Since this has integral coefficients and the discriminant is equal to 0, there is a rational double root. Okay, for the next 3 examples, we're given an equation with variable coefficients, and we need to figure out what those variables should be in order for us to have, first, a real double root. Okay, so I'm going to note my a, b, and c. So a is equal to k, b is equal to 12, and c is equal to 9k. I'll also note that if an equation has a real double root, my discriminant is equal to 0. So I'll set my discriminant equal to 0. I'm going to move some things around, okay? And I solve to get that k is equal to positive or negative 2. Same equation, but now we need to find 2 different real roots. In this case, we need our discriminant to just be positive. So we're going to set it greater than 0. Move things around again, and we get the absolute value of k has to be less than 4. Now, be careful. You can't just solve this like a linear equation. When we take the square root of an inequality, we have to set an absolute value. So the absolute value of k has to be less than 4. That's a compound inequality. Think about it like your barbells. It's between 2 values. So k has to be between negative 2 and positive 2. Finally, we have the same problem, but now we need imaginary roots. Okay, so what happens when we have imaginary roots? Very good. D is less, that's a mistake. D should be less than 0. So I'm going to set up the same equation, but it should be less than 0. Move same things around. Have another compound inequality, but it's an or statement this time. K can be less than negative 2 or greater than positive 2. So in closing, can you remember the 3 cases of the discriminant and the nature of the roots for each case? Feel free to turn to your classmate, chat about it, and I will see you in the next lesson.